we can move on. Right. So now we need to find a value. Let's see. I'm pretty sure this is back to being a D word, a 4-byte value. Read double goes back to being read integer. It's a 100. Change. Now it's 994. Oh, wait a second. We still have this set to decreased value. So we need to change that to exact value here because it's not decreasing. So current value is 994. Change it. 408. And we have one result right there. Right. So now what we need to do is find some code and change it. So this code isn't going to help anymore because all it does was find this address. Right. So our address equals this as hex. Actually, let's leave that as a string. And again, I wrote some code earlier. Not step 3, we already did that. Right here, step 5. And I have the address. Right. So what it does is it first checks, are we already debugging the process, which we're not because this is the first time we're doing anything. And if we're not, then it calls debug process, which again is right here in the documentation, debug process. Right. It starts the debugger for the currently open process without asking the user. Optionally, you can provide what type of debugger to use. So if you go to settings and then debugger options, you see it has Windows and kernel mode debugger and VEH, and you can pass those right here, right? Or you can give 0 or nothing to use whatever the default is, presumably whatever's set. And then we're creating a table because what we want to do is basically duplicate in a little bit this right here. What is accessing these values? Oh, we didn't write the address in there. That's why nothing showed up. I should do that. Properly demonstrate. Right? See, we want to get these values, these addresses and instructions using Lua. So what we're going to do is we're going to create a table to store that information is, and then we're going to say remove breakpoint just in case there was one already. So if we're running this multiple times while testing, it'll remove that breakpoint and then add a new one. And we're going to set breakpoint, which again, right in here, is debugging, get current interface, can break, is broken, set breakpoint, remove breakpoint, continue from breakpoint. All right there in the documentation. Actually, let's leave that up for a second. So when we set a breakpoint, there's actually several ways we can do it. The one I'm using is we're giving it an address, the size to check, the trigger, which is, I think that's explained here, BTP. No? Okay. You can go to defines and you see they have breakpoint access, breakpoint execute, and breakpoint write, which is basically what's over here. You can find break what accesses it and you can break what writes. Or when you're actually in here, you can set a breakpoint and that breaks on when it's executed. Data breakpoint, right? And access. So that's where those values come from. And then you can pass it that's a breakpoint method, which is whether it's hardware or software, but we're using this one here, which just skips that and gives it a function to call. So when this breakpoint is hit, it will run this function right here that we're passing to it. And it doesn't get any arguments. But what it does have is the registers, right, as variables. Let's see. I think that's mentioned above. Yeah, debug variables. You get e-flags, you get these registers. So you can access all that information from Lua when a breakpoint is hit. They aren't valid in between. You can't access the registers when you're not on a breakpoint because they're constantly changing because the code is running. So when we hit a breakpoint, what we do is we go, hey, what is the opcode, right? We want to know what is the instruction that actually ran, right? So it's the previous opcode because it's already ran at this point. So if you go get previous opcode, there's also get instruction size and disassemble to get information about code based on an address. Now, while it says this is just an estimated guess, it is pretty accurate. And then once we have what that instruction is, we store it. We store it in there if it's new, or if there's already one in there, then we store that, right? We're storing 0 for how many times it's been hit and the instruction itself. So if it's there, then it keeps that. And we increment how many times it's been hit, how many times that instruction has ran, and then we store it back in there. And we print it out just so we can see it. So if we go over here and we go Control B, you'll see we have a breakpoint now that we didn't have before, not that you could see it. And if we start changing the value, you can see it's pulling up information, right? And if we come over here and add our own, right, you'll see hardware breakpoint, and this time you'll see that it's a different type of hit. It actually can show that it's find breakpoint, and because we have our own here, then that messes with the cheat engine. But if we run that to remove ours, then we start running it. See, there you go. And you're actually getting the exact same information right here. You're getting the count of how many times it's been hit, you're getting the address, you're getting the bytes, and you're getting the instruction. So what do you want to do with that? Well, we want to find the one that's writing to our value and map it, right? So you can come over here, you can view this information. You could use this disassemble from Lua to do it all yourself, but I'm not going to go that far. So what we want to do is we want to take the address that we got over here, and we want to write a NOP to it, right? Write bytes, this address, and NOP is hex 90. And actually, let me copy these. The original are 89 and 90. 89 and 10, my bad. Alright, so execute this. You see this change to 90. Right, and now nothing happens. Our value does not change, which is exactly what we wanted. Now, if we come over here and change them back, I can show you another method of doing this. Probably slightly easier. Right, so now we change that back. Now what you can do is there's a function called auto-assemble. And you will find it in here. And you pass it text, which is a script, just like if you went over here and you created an auto-assemble script. And right. So this is the kind of script we're going to run, right? This is what we're passing to this function. I don't remember if I had one set up already. It does not look like it. I don't think I saved it. I did over in step 7, but so we'll just create our own. Enable, disable, and not there. What is the instruction? The address right there. And we want to write NOP. And honestly, this disable section isn't going to run right now because we have no way to disable it after this. There is a way, I will show you, but just to show that. Did I do it wrong? Is this not the right address? Maybe it needs this disable. Yeah, there it goes. It needed to be a valid script. Now, if you look over here, it says it returns true on success with as secondary a table you can use when disabling. Right? So that's what we'll use to disable later. And if I was checking whether it was successful, we'd have seen that why it wasn't. So, but now right now we didn't save that information, so there's no way to properly disable this. So I'll just come over here and type in db8910, which I'm pretty sure is what was there before. And we can move on to the next step, which is pointers. So honestly, I'm not going to go through this one with Lua, because if you've understood what I've said so far and you know how pointers work, you know you find this value and then you find what accesses it and then you find that value and you just keep going multiple times, right? Until you get the base address, which you've already seen enough to do that. So we're going to skip that. Even though you say boo, that's fine. And this one, we're going to show a more advanced script that lets you actually disable it, as well as generate your own, right? So let me get rid of this part. Let's say we've already found where we want to change, right? We have this, and normally we'd go tools, auto assemble, and then we'd use a template, right? And that's how we'd get our script. Well, you can do the same thing in Lua. You can come over here, you can have your address, and then you can create what's called a string list that will hold your script. Pardon me. And you can call this generate AOB injection script. And they're in here. There's one for API hook right there. / generate. And there it is. Code injection, AOB injection, and full injection. And you give it this script, which is a type of string list, which will just has various ways to handle strings, right? And you give it the symbol name you want to use, just like when you type it in, it prompts you what name do you want to use, and you give it the address that you want to generate the script for. And then you just print out what that text is, what that generated script is. Right there. Let me make that bigger. But there's your AOB script that would be generated if you did it in the GUI. With the script does blah blah, it has the author, and all that. So then you can copy and paste that into the call auto assemble. And then that'll work. Let's see, let's pull our view back up. Let's enable it. And you get the jump. You get whatever it got changed to. Apparently I changed it to add to. You can jump back. And let's see. Well, I guess I should show at the top. You can see that we're storing the result this time for whether it succeeded and the disable info. And you can see that we printed out that disable info. So you can see that it has one registered symbol, and that's called inject, which is what we gave it when we created the script. I don't have it in here anymore. If I go back over here, you can see I gave it inject. And what got allocated was a new mem, which you can see right here. And you can see the size. And you can see what address it got allocated to, 1D0, which is where it's jumping. Right? So that's what autoassemble uses to disable the script. So if we actually run this again, I'm passing that disable info here. You can see that it gets disabled, and it goes back to sub 1. And then we can run it again. And we pass step 7. And then step 8 is, again, pointers, which you already understand how to find. Well, if you understand how to find pointers manually using this method, not using the pointer scan, because you don't actually understand how that's working. If you can go in here, you can go 4 byte, and you can scan for 780 and change that. And then you go, what is accessing this? And you can come over here, ESI, and scan for what address stores this, and keep going until you get a static, which that's wrong for this step, right? That is not the base address here, because this is a multi-step, multi-level pointer. Wow, this is a long video. My throat's getting really dry. But we're almost done, right? Actually, I think we might be done except for a couple extra things I wanted to cover. Because step 9 is really the same thing. You scan for values, you find what's changing them, you write a script. Nothing new there. So, a couple of the new things I did want to show, I have listed over here, are doing an AOB scan, right? Because those are useful. Maybe you don't want to create an actual script. Maybe you want to do an actual AOB scan in Lua, right? So that's equivalent to coming over here and doing AOB scan. And this is executable, I think. Yeah, executable, so not writable. I hope that's unique. Really? Will that help? Apparently not. Okay. So it's probably this that I was finding. Actually, that's probably what's going on. Let's see. Control Shift. I messed that up now. Okay. Let me get the step 7 script back up so we can disable it. And then our AOB should work. I don't need the documentation right now. Again, all this info is listed in the documentation. There we go. You can see that it's here. All right, so we're scanning for this AOB. And 83AB784, blah, blah, blah. And if it returns no results, if it fails, then it would say error AOB. So if I just put some random crap in there, you'll see it failed to find the AOB on line 5. And then we loop through those results. It returns something like a found list. It actually returns a string list. If you remember when we created the script with the generate script function call, and we created a string list and passed it to that. That's what these returned is a string list. But we loop through there, we print the result, and we print the type just to show that it is a string. This address is actually a string that it's returning. So if you need to add 4 or something, you'll have to convert it to a number first. And then we destroy that results. And there are several ways to do this AOB scan. You can use this one where you pass a list as parameters, basically. Or you can pass it as a string. And there's also one that lets you use these protection flags. If you'll remember, the memscan actually referred you to the AOB scan for the protection flag information. And then you can always fall back to that huge memscan option where you come in here and you basically choose array of byte. And just like when the first couple steps. So that's how you can do AOB scans in Lua. And then we have a timer, which lets you do something multiple times, or at least after a delay, which is what this one does. It waits 1,500 milliseconds, and there's 1,000 milliseconds per second, so that's about a second and a half. And it prints a string, which apparently is konnichiwa. So the way that works is you create a timer, and then you set the interval for how long it will wait in between each call. And you give it a function to call every time that time is up. And that function will take a copy of the timer that was created. So you can call destroy for it to only run once, or you can say sum counter equals 0. Let's copy that. Sum counter equals sum counter plus 1. If sum counter is greater than 5, then we destroy it. And let's make that faster, right? So then it runs 6 times or so, and then it stops. Now, one useful thing I've found for that is to disable scripts yourself, right? To have a script automatically disable itself. So a lot of the times you'll write a quick script where, say, you just set a static value. Let's use 400/290 because I know where that is, and it won't mess anything up. Right. And you don't do anything in disable. You just want to set this value. But you want to make it so where all the user has to do is click once and it's done. Well, you can come in here and you can use Lua code, and you start that with this curly brace $Lua, and then you can create a timer here that runs after a very short period of time, only 1/10 of a second here. And you destroy that timer because you only need it to run once. You can say if not syntax check, then memrec.active equals false, right? And what this is doing is saying if we're not doing a memory syntax check when we're saving the script or editing it, then what we want to do is access this memory record and set its active property to false. And actually, that is the memrec variable is one thing I don't think you'll find in there, and syntax check either. But you can find, if you go to the documentation, which I've closed. Good thing I have it pinned here. Memory record. There's not the hotkey, the actual class itself. You can find a bunch of information right here. But if you look at active, not action, you'll see that as a Boolean, and if it's set to true, it will activate or freeze memory values. So if you have something over here like this, setting it to active will freeze it, whereas if you have a script, it will actually activate or deactivate that script. So what setting it to false does, it will deactivate the script. And then you use these curly brace $asm to close this Lua segment. So if we come over here, you can see that it closes itself. But it is actually running, right? It's not that it failed to run. Did I type that right? 400/290. There we go. There's the knobs I expected. So if I change this back to 0, 0, 0, okay. That did not give me the zeros I expected. 400/290 db 0, 0, 0. There we go. And then we run the script. You can see it puts in NOPs, and it's already disabled. So that's a nice thing I've found in a few scripts, few tables of my own. Like, I want scripts that will self-disable. Let's see, what else was there? I'll implement those. I didn't put it in there. Okay. One other thing I've found useful is you can return a string here. And what it does is it will actually be turned into autoassembly code. So I can come up here and I can delete that. And I can come over here and say db for define byte. And then I want to do string.rep, I think, 90 for the space. And I want to repeat that 12 times, let's say. And if I got that correct and enable it, what you'll see is I get 12 not bytes, right? So this gets turned into the code. Well, if I just print that, actually. And without the syntax check, you'll see that it's actually running. Unexpected symbol. All right, because it's a function call, not Python 2. Right. And yeah, you'll see. See, I haven't activated the script, but I hit OK, and that syntax checks runs the code. And you'll see this is what it got turned into. So it's the same as if I had typed that in there like that. So I've found that useful on occasion, particularly for knopping long, a lot of instructions. There are plenty of other uses for it. Back to general. Manipulating a memory record. Hopefully I copied that correctly. I'll just run that here, I guess. I'll put it in the script. Why not? So what this does is it gets the address list, which is this full thing, and there's a function called get memory record by description, right? So we store that in case we want to use it multiple times. It's faster to use a local variable than it is a global variable like this. And we call that to get a specific memory record. In this case, we're using one that's called test. And again, I use 400/290 here, and we'll call it test. And we'll set that value to 0. Because what this timer does is it runs and increases it by 1 until it reaches 100. So if I go over here and I activate that, you'll see that it starts increasing by itself. And when it reaches 100, and when it's greater than 100, which is 101, it stops. And we could actually throw in a memrec.active equals false to disable the script. So let's set this down to 90, enable it, and there you go. It disabled itself. So that's also something I've found is occasionally useful, but mainly it's the information about how to change memory records here, right? There's addresses and colors and whether it's shown as hex, whether it's allowed to increase or decrease. You can toggle all that with a quick memory script if you know the name or if you know the ID number, right? Because there is a get memory record by the position, which is just get memory record. It will get it by the position in this list. I don't recommend using that because it's really easy to move things around and then that breaks. But you can also get it by the description, as I showed. But unless it's a trainer, then somebody can go in here and change that, and then your script breaks. Oh no! Right? And come over here and go show on print. And put this back to test. And attempt to index up value MR. Oh yeah, because we queried it up here. So, oops, that's just going to keep running forever now. And well, until Cheat Engine is restarted. Actually, did I have this destroy itself? It doesn't look like it. Let's see. So, you can also get it by the ID, right? Which you could either open the cheat table as a text file and get the ID that way. It's stored in the file, and it's just a text file, even though it's .ct. Or there is a little extension called extra memrec info, I believe. I can double check real quick. Yeah, extra memrec info that you can find on the forums, and it will show you the ID right here. It will also show you the index, the number of children, whether it has hotkeys, how many hotkeys it has, what the address is. Kind of useful. Mostly I use it for the ID. That way I don't have to open up the file. change records. Let's see. I think that was all I wanted to mention there. Yeah. I did put this in here. Good. So, as you saw, I created that little mistake, and now we've got this constantly printing out errors. Not good. I haven't used this method myself, but what you can do to prevent something like that is use pcall, which, if you know Lua, you probably know this. It stands for protected call, right? So we're doing the same thing right here, but now it's being inside of a yet another function call. And so what pcall does is if there's an error, it will actually stop it from going all the way up and causing a real error like this. And it just returns true or false and what the error message was. So if you use this pattern, then if it messes up, then you can say you can just destroy the timer so it doesn't keep running. Wow. That is a really long video. Hopefully it's not so long that it's not useful. But just to reiterate, the main purpose of this video is to point you to this documentation. I don't mind answering questions if anybody has any. Feel free to ask. But most of what you need to know, or might want to know, is sitting right here waiting for you to read it. Or just do searches. So, hope that helps somebody. And see you next time.